Okay, ji, Bismillahirrahmanirrahim. Let's start. Today we are going to revise a bit about the resistance we did before. So, resistance of a cylinder was L is equal to L, R is equal to L by conductivity multiplied with the cross-sectional area. So, where L is the length and A is the cross-sectional area. And what is this? Sigma is actually showing us the conductivity. In fact. And that's how we calculate the resistance. In fact, we considered a small cylinder, and in that cylinder we applied, in fact, this was point A and this was point B, and we applied voltage, higher and lower potential over here. The direction of E was in this, from higher to the lower potential, and the current density was also in this direction. So now, if we want to find out the power density inside the conductor, if this is a conductor and we want to find out the power density inside the conductor, so how can that be done? Is simply you multiply E, you do the dot product of E and J, where E is a vector and J is a vector as well. So it's like volts per meter, and multiplied with amperes per square meter. So that gives you actually what? Watts per cubic meter, right? So this is how you obtain the power density inside the conductor. So let us find out what it is actually. So J, we knew that from the Ohm's law at a point that it is sigma E, and then we can also say that it's sigma E square, and the total power dissipated in conductor is found by integrating it. So this was for a differential surface, but now if you want to find out the total power dissipated, in the conductor, is found by integrating the power density, over the whole volume, in fact. So the total power dissipated is actually equal to P, which is volume integration of E dot J and differential volume, right? So then it becomes, if I say it is, in fact, if the value of E is E and the value of J is J, I mean the scalar value. So we get the, after the dot product, we get this one, and then we say E, and then we go on and we say E is it's the line integral, in fact, and due to the surface we can say, because volt iske unit jo hai na, that is volts per meter hai na, and the unit for this is amperes per square meter, right? So I can say J dot ds, so J dot ds, which is actually for the surface current density, and this is electric field intensity. So we knew that it's really interesting to find out that this is actually equal to V, and this is actually equal to I, right? Anyone, any question? So this is amperes per square meter multiplied by the meter square, and this is volts per meter multiplied with the meter. So that gives you volts, right? Which is in fact the voltage, and this gives you the ampere, which is actually the current. So that is actually equal to the power dissipated. So in fact we derived the circuit theory formulas using the electromagnetic field theory.